so today we're going to do an APBC topic, which is finding the speed of functions in parametric terms, right? So functions where you have horizontal position x of t and vertical position y of t. So we've learned before that that x of t is our position, right, relative to the origin on the x-axis, right? And that y of t is our position, but relative to the origin on the y-axis, right? So on the y-axis, meaning vertically, right? On the x-axis, and it is a directed quantity, meaning it is a vector. It has a direction. You can have a negative position. So we've learned that x prime of t, right, is the velocity. Again, that horizontal velocity. So I'm just going to put an h next to it for horizontal. And that y prime of t is my velocity and vertical. So I'm going to be lazy and just put a v behind it for vertical. All right. So again, we have horizontal position and horizontal velocity. We have vertical position and vertical velocity. And then we could derive again and find acceleration. So what you may remember about speed in general, right? So these guys together are my velocity. What you may remember about speed is that speed is the absolute value of velocity. But when we talk about vectors, which is fundamentally what's happening with parametric equations anyway, absolute values of vectors are a little bit unusual. So let's take a little bit of a tangent note, right? So like we're going to go off tangentially, and not tangentially specifically in the math sense. I mean, it is, but quick tangential. If you have some vector, v, that is a comma b, right? And you want the absolute value of that vector, the way that you find that absolute value is essentially by doing the square root of a squared plus b squared. That's the absolute value of a vector. Basically what's happening is if you think about the vector where it has a direction A and a direction B and you want to find the length of this V, it makes sense that what you're fundamentally doing is the Pythagorean theorem. So the reason I threw that tangential in is the same thing is happening here. So if you picture my overall velocity of something that's moving parametrically, it's got some velocity in the x direction, it's got some velocity in the y direction. So if I wanted to find the magnitude only, the physical size of its motion, right, of its velocity, but I wanted the size, meaning just the speed of it, the absolute value, I would basically do Pythagorean theorem, right? So if I wanted to find the speed, what this numerical value was, I would do Pythagorean theorem. I'd do x prime of t quantity squared plus y prime of t quantity squared equals speed squared. So if you think about it in that sense, what you get is speed squared equals my x prime of t quantity squared plus my y prime of t quantity squared. And then when I go to solve for speed, I get that speed, without the need for plus or minus, because it is a scalar, so it's only positive in this situation, it doesn't have direction, is my x prime of t quantity squared times my y prime of t quantity squared. So again, that's our formula for speed in parametric mode. It comes from essentially this formula that we use for vectors, but you can also see the logic of it if we were to draw a diagram of my net motion being both this way and this way, right? I'm horizontal and vertical, and if you picture that as a right triangle, you can see how we end up using Pythagorean theorem. So anytime you're asked to find the speed of a motion, of something in motion parametrically, right, some particle that is written as x of t and y of t, you're going to do it by doing the square root of the quantity x prime of t squared plus y prime of t squared. Interesting side note, you might recall that arc length, right, oh, that's not, I don't know, I added a letter, guys. Ignore my inability to spell words like arc. It's cool, it's not like it's a huge part of my job. Recall that arc length, let's say from t equals a to t equals b, was just the integral of this exact same thing. And you might think, hey, that's weird. How does that relate? Why is that happening? That's super bizarre. But it's actually not bizarre if you think about it, because how'd you find total distance way back when we weren't using parametrics, right? The laziest and easiest way to find total distance was to integrate the speed, right? To integrate the absolute value of velocity. So if we just want to make a quick little connection between arc length and velocity in general, right? Way back when, right, in non-parametric stuff, let's say that v of t was my velocity, right? Which means that, again, in non-parametric stuff, the absolute value of v of t is totally my speed, right? And so if you were doing old school particle motion questions before BC, before you knew anything other than AB calculus, if I asked you to find the total distance, the easiest way to do it if you had a calculator, right, the total distance on some AB was to integrate that speed from A to B, right? That was the easiest option. Well, now what I'm telling you is if we do the same problems, the same context, but instead my velocity with respect to time is actually written as two different kinds of velocity, my x prime of t in the horizontal direction, right? That's velocity in the horizontal direction, and my y prime of t, which is velocity in the vertical direction. And that my speed, the absolute value of velocity, is that formula we just learned, x prime of t quantity squared plus y prime of t quantity squared, right? It's not at all surprising that the way you'd find this total distance, which for the record is exactly the same meaning as arc length, again, for some reason, I can't spell the word arc, on some t equals a to t equals b, is the exact formula we learned like 3 videos ago, right? So again, totally interesting, sensible, in context of everything you know about AB Calc and also everything you know about vectors. Cool. One last thing worth throwing out there is that the other way you might see this notation, just as a side note, is you might see x prime of t as a dx dt, right? And you might see y prime of t as a dy dt. So don't be thrown if you see that notation instead, where this is dx dt quantity squared and dy dt quantity squared.